Okay, good morning, everyone. So today we will still discuss about still the introduction part of our fluid mechanics class. And last week we have discussed about viscosity. So basically, if you want to learn in details about viscosity, you can check the EduNext. I have uploaded one good explanation from YouTube about the understanding the concept of viscosity. And actually later when we discuss about friction in fluid flow, then we will visit this concept again. So basically, there are two main difference. There is main difference between liquid and gas viscosity, where for the gas, when you increase the temperature, the viscosity will also increase, but for the liquid, the viscosity is decreased when you increase the temperature. It is due to the reason why the viscosity raise up for each gas and liquid is also different. Okay, relating to viscosity, we have two, maybe it's easier to explain using this graph. Basically, any fluid can be categorized into two different characteristics based on its viscosity properties. One, we call it Newtonian fluid. Newtonian fluid is the fluid that follows Newtonian law. This is the Newtonian law. It says that this is in the Newtonian law. It says that shear stress is stress is a similar concept with pressure. So force divided by area. However, the area is the not cross-sectional area, but the surface area. So for Newtonian fluid, whenever you increase the shear stress, the rate of deformation will also increase. So for easier understanding, you can think the rate of deformation is the rate of how fast this fluid can flow. Ya, jadi laju deformasi ini Anda bisa artikan secara sederhana sebagai seberapa cepat si fluida itu bisa mengalir. Karena sebetulnya actually rate of deformation fluid is said to be flowing. It is because it experience continuous deformation. Ya, jadi sebetulnya yang disebut dengan mengalir itu adalah fluida disebut dengan mengalir adalah fluida tadi mengalami deformasi kontinu. You may check the video. What will be the differences between fluid and solid when they undergo deformation. It is said that for fluid, the deformation occurred due to shear stress. For fluid is happen continuously. So rate of deformation, you can easily understand it as rate of flowing. So increasing shear stress, it means you increase the rate of flowing fluid. Jadi ketika Anda menaikkan shear stress, sebetulnya Anda akan menaikkan laju mengalirnya si fluida. So for the Newtonian fluid, it always proportional between the shear stress and rate of deformation. Of course, it will be depending on the characteristic of the fluid. So this is the example of three Newtonian fluid, which is air, udara, water, and oil. All are proportionally increased between the shear stress and rate of deformation. However, the slope or the gradient between the shear stress, the curve of the shear stress and rate of deformation is different. You can see for the air, the slope is very, very small. So it means you slightly increase the shear stress, the rate of deformation will increase significantly. In contrast, for oil, when you increase the shear stress, the rate of deformation doesn't increase significantly. So you need much more shear stress when you want to achieve the same rate deformation for oil as compared to air or maybe water. So this ratio, the gradient, between the shear stress and rate of deformation, that's we call it mu. Mu is the viscosity or the absolute viscosity. You can see this one. So the graph between the shear stress and the rate of deformation for Newtonian fluid will be starting from 0, and then the curve is linear straight line, and the gradient will be the viscosity. The higher gradient represent higher viscosity, then it means the fluid is more difficult to flow. Bisa dipahami ya, jadi kalau untuk fluida Newtonian, kurvanya akan seperti ini, bentuknya garis lurus, dimulai dari titik 0. Nanti semakin shear stress-nya naik, laju deformasinya akan naik. Tapi kenaikan laju deformasi itu akan bergantung pada viskositas. Untuk fluida yang viskositasnya tinggi, di sini contohnya adalah oil, untuk mencapai laju deformasi yang sama, butuh shear stress yang lebih tinggi. Higher shear stress means you need to apply higher force to have the fluid experience the same of rate of deformation. Okay, this is the concept of viscosity, or the absolute or dynamic viscosity. Mu is the dynamic and or absolute viscosity. So the second category will be non-Newtonian fluid. Non-Newtonian fluid is the opposite of Newtonian fluid. So it means shear stress and rate of deformation is not linearly proportional. Ya, jadi untuk fluida non-Newtonian, shear stress dengan laju deformasi ini tidak linear, tidak proporsional. What is the correlation between shear stress and the rate of deformation? It will be depending on the fluid, because there are many types of non-Newtonian fluid. So this one is the Newtonian one. So sometimes you will experience, depending on the fluid types, so some fluid will experience like you increase the shear stress, the rate of deformation is still 0. It means increasing the shear stress doesn't make the fluid to flow. Ya, for this Bingham plastic, ketika Anda menaikkan shear stress, laju deformasinya masih 0. Artinya fluidanya belum bisa mengalir. So you need to achieve a certain amount of shear stress, and after this amount is achieved, then you increase the shear stress again, then the fluid, the Bingham plastic fluid, will start to flow. And for the Bingham plastic, the curve is similar with the Newtonian fluid. So it's increasing proportionally, but doesn't start from 0. Ya, jadi yang untuk Bingham plastic ini profilnya mirip dengan yang Newtonian, garis lurus, tapi mulainya tidak dari titik 0. Butuh nilai shear stress minimal sampai si fluida ini bisa bergerak. Kalau yang Newtonian kan dari 0 ya, jadi begitu dinaikkan shear stressnya dia langsung bergerak. For the Bingham plastic, it needs a certain minimum value of shear stress. Okay, how about the others? You can see from the curve. So for the pseudoplastic and dilaton, it will start from 0. It means when you increase the shear stress, the fluid start to flow. However, the rate of deformation is not proportional. Sometimes, like pseudoplastic, when you increase the shear stress, this one, it become thicker and thicker. So the rate of deformation, this one become thinner and thinner, and this one is become thick. This one become thinner and this one become thicker. So it's not like water or oil when the viscosity is constant, but this one depending on the shear stress. Later, in the last weeks in our class, we will discuss about this non-Newtonian fluid in more details. And sometimes the viscosity, since the value of viscosity is not constant like Newtonian fluid, right? So for non-Newtonian, the ratio between, or the gradient between the shear stress and the rate of deformation, we call it apparent viscosity. Okay. Okay, and then from the video, I hope you already watched the video. And sometimes, since viscosity is influenced by pressure and temperature, especially for the gas, in some calculation, we express viscosity not as absolute or dynamic viscosity, but we express it as kinematic viscosity. Ya, jadi untuk beberapa perhitungan, beberapa kondisi, khususnya untuk gas ya, karena gas itu sangat dipengaruhi oleh tekanan dan temperatur, maka untuk beberapa perhitungan, dynamic viscosity is changed into what we call kinematic viscosity. So kinematic viscosity is the absolute viscosity, the dynamic viscosity divided by the density at that pressure and temperature. You still remember, right? For fluid, the density, especially for the gas, the density, the volume of the gas will be depending on the pressure and temperature. So the density will also depending by the pressure and temperature. So at certain position of pressure and temperature, we can express the kinematic viscosity as mu divided by density. So you can compare air, udara, at 293 Kelvin and 1 atm. You can compare the value between the, please pay attention to the units for mu and for kinematic. So the value between dynamic and kinematic viscosity is slightly similar. This is the normal condition, like 20 degrees C, not normal. Yeah, room temperature is slightly lower than room temperature and normal pressure, atmospheric pressure. But when you increase the pressure 4 times, become 4 atm, still at 20 degrees C, you can compare that the kinematic viscosity will reduce. The dynamic viscosity is still the same. The absolute viscosity, the mu1, is still the same at both pressure, but since the density is different, then the kinematic viscosity is also different. Okay, there are two equipment, apparatus, that you can use to measure the viscosity of certain fluid. One is called capillary viscometer, or we call it Oswald viscometer, and the other one is falling ball viscometer. I have also, I won't explain the principle of this equipment in details. You can see you can watch the YouTube video, and actually later in the next semester, you will have experiment in order to calculate liquid viscosity. Okay, and this one you can also watch from the YouTube video, that to express the correlation between the viscosity as a function of temperature, there are several equations that you can use. Like for the gas, you can use Sutherland correlation, where the value of A and B is already stated for the atmospheric condition. But of course, if you measure the viscosity at different atmospheric condition, you will need to get the value of the constant A and B. Where you can get the constant, you can check from the handbook, the chemical engineering handbook perhaps, or mechanical engineering handbooks. Also with the liquid, you can use certain equation to measure the absolute viscosity. This is one type to get the value of fluid viscosity. Other means to get the value of the viscosity, of course, you can check from the graph. This graph is generated from experiments. So you can just check. It will be very specific for certain types of fluid. For example, this is for dry air. This is the dynamic viscosity. You need to pay attention to the values and units involved. Ya, jadi kalau Anda membaca grafik, if you read graphs for the table or equation, of course you need to check the units as well. For the graphs, you need to pay attention more to the units and also the value. Like for this one, the viscosity will have the units value of micro mu in I don't know whether it should be in micro Pascal second, and the unit of the pressure will be megapascal. And also for this one, and this is for dry air at different temperature. And this one is for water. Water, we get the value between, if this one is between pressure and mu, and this one is between temperature and mu. Or sometimes you encounter what we call nomogram. Nomogram is another tools or another graph that you can use to get the value of the viscosity. How to get the value? Basically, beside this graph, it will be included with the table. What is the table? The table is the coordinate between x-axis and y-axis for certain compounds. For example, certain fluids, certain whether it's liquid or gas. So I suggest you to read carefully the title of the graph, but I think it's the letter is very small. This is the nomograph for gas. Ya, jadi ini kalau Anda membaca nomogram, Anda perlu baca dulu judulnya, apakah itu untuk gas ataukah itu untuk cairan. So first, you need to check whether it's for the gas or for the liquid, and then you need to check the unit and the value of the parameters involved. For example, this one between temperature. Jadi ini mengukur viskositas. The viscosity is here in certain temperature. How to get the value of the viscosity? Because this is the value of the temperature. This is the value of the viscosity. So you need to check. I think the table is not written here, but actually for certain gas, there will be one table that stated, for example, for the ammonia, it will be like 12 or 13 for the y-axis and 10 for the x-axis. Jadi contoh saja ya, saya juga nggak hafal angkanya. Misalnya gas amonia X-nya 10, Y-nya 13. X is at 10 and Y is at 13. So the position will be around here. So this is the position for certain types of gas. So if you want to know the value of the viscosity, you just make a straight line between the temperature to the position of the gas. And then you get the line will be crossing the value of the viscosity. Kebayang ya? Jadi katakanlah saya nggak hafal, ini mungkin gas amonia gitu ya, posisinya 10 sama 13. Untuk dapat nilai viskositasnya, Anda tinggal tarik garis lurus saja. Misalnya pada temperatur 70, ya tarik garis dari 70, memotong tadi ya 10,13, terus gitu sampai memotong sini. Nanti dapat angkanya. And then you need to pay attention for this value, what will be the units of the viscosity. Whether it's in centipoise, whether it's in Pascal second, or in other units. Okay, any question until this part? Silakan, ada yang mau bertanya? Cukup jelas ya? Okay. Then I will continue to another properties. This one is surface tension. I think for this one, I won't go to details. So basically, surface tension is the tension that exerted by the surface of certain fluid, especially liquid, right? Maybe in your high school or TPB, you will still learn the concept of cohesion and addition. Yeah, the one is between the same molecules. Cohesion is the interaction between the same molecules. For example, molecule water and molecule between water molecule. And addition is interaction between different molecules. Water with solid, for example. So if the interaction of addition is higher than cohesion, then it will say that the fluid will istilahnya membasahi ya, it will be wetting the surface of the solid. The example of the liquid is water. Jadi untuk air, interaksi dengan padatan itu adhesinya jauh lebih kuat daripada kohesinya. Kalau kohesi itu interaksi antar molekul airnya. Sehingga air akan lebih membasahi padatan. The other case is mercury. The mercury, the cohesion will be much higher than addition. So when you pour mercury liquid into some solid, they will create this kind of surface. It's called non-wetting liquid. But again, it will be depending because cohesion is between the same molecules. Yeah, cohesion is same molecules. Addition is different. So for the addition, it will be depending on the liquid and the solid properties. Okay. Okay, how to calculate surface tension? I think there are several videos that you can find to get the methods. Okay, and the value you may check, you can get from the handbook as well. So I won't discuss it very in details. And the last one is about vapor pressure. So it will be, I think, you will have this detailed discussion about vapor pressure in thermodynamics class. So I will just explain in briefs. So basically, when you increase the temperature, yeah, at certain pressure, pada tekanan tertentu, if you increase the temperature, the molecule of the liquid, yeah, the phase of the liquid molecules will start to change into vapor. Yeah, the more you increase the temperature or the longer you keep the increasing temperature condition, then more water molecule, for example, will change into vapor. It means the phase is changed into gas. Okay, at certain point, there will be a balance. Balance means equilibrium between the vapor phase and liquid phase. Ya, jadi pada kondisi tertentu, kalau misal tadi kan ketika Anda menaikkan temperatur, terus dijaga pada temperatur tersebut, gitu ya, itu kan nanti kan dia akan menguap. Sebagian molekul akan berubah menjadi uap. Some liquid molecules will change into the vapor molecules, and also some vapor molecules will change back into the liquid. Jadi ada yang berubah jadi uap, sebagian ada yang berubah lagi jadi cair. At certain point, it will reach the equilibrium condition. It means the pressure that exerted by the liquid molecules will the same as the pressure that exerted by the vapor molecules. It's called the equilibrium condition. Okay, At this equilibrium condition, we can say that the vapor pressure, the vapor pressure, or we call it tekanan uap in Indonesian, pressure vapor is the pressure that is exerted by the vapor substance when it is in equilibrium with the liquid phase. Ya, jadi yang disebut dengan tekanan uap dari suatu cairan atau dari suatu fluida itu adalah tekanan yang dihasilkan oleh uap dari fluida tadi ketika berada dalam kondisi kesetimbangan. Kondisi kesetimbangan itu apa? Kondisi di mana ya tadi ya pertukaran fase antara cair ke uap dan uap ke cair itu seimbang. Jadi sebagian berada dalam kondisi cair, sebagian dalam kondisi uap. Nah, pada saat kondisi kesetimbangan tadi, tekanan yang dihasilkan oleh uap-uap ini yang kita sebut dengan tekanan uap. This we call it vapor pressure. Saturated vapor pressure, saturated pressure or saturated vapor pressure is actually the vapor pressure, but it's the term to mention the vapor pressure of the pure substance. Jadi yang disebut dengan tekanan jenuh atau tekanan uap jenuh itu sebetulnya ya tekanan uap tadi, tapi lebih spesifik pada kalau senyawanya atau fluidanya adalah fluida murni. Jadi air saja atau misalnya nitrogen saja, oksigen saja. So for the pure substance, we call it the vapor pressure is also called as the saturated pressure. Why we call it saturated? Because at this point, at this pressure and temperature point, the vapor and the liquid are in equilibrium. So we call it saturated. Jadi sebetulnya sama ya, antara tekanan uap dengan tekanan uap jenuh itu sama. Kondisinya sama-sama pada saat kesetimbangan, hanya saja tekanan uap jenuh itu untuk menyebut kalau fluidanya adalah fluida murni. It's for pure substance. Okay, how to get the value of vapor pressure or saturated pressure of pure substance? We can use a certain equation. Normally, we can use the Antoine equation. So Antoine equation correlate the vapor pressure of certain substance at certain temperature. Then you can get from the handbook what will be the value of A, B, and C. These three, A, B, and C, is the constant. We call it the Antoine constant. But please pay attention when you read the handbook again. When you read the handbook, you need to pay on certain aspect. So between pressure and temperature, then you can get A and B and C value from the handbook. You have to make sure, or you have to pay attention what will be the unit of the pressure and what is the unit of the temperature that you need to use. Ya, jadi ketika Anda menggunakan persamaan Antoine untuk menghitung vapor pressure atau saturated vapor pressure, ya, nanti kan di buku Anda akan lihat, oh persamaannya adalah A, B, persamaannya ini, nanti untuk zat nitrogen, ABC-nya berapa? Oksigen, ABC-nya berapa? Gitu ya. For the nitrogen, what will be the ABC? The nitrogen would be ABC. It will be different. Jadi Anda perlu lihat satuan, ini kan bentuknya angka ya, A itu nanti angkanya berapa, B-nya berapa, C-nya berapa, untuk zat-zat tertentu. Nah, Anda perlu pastikan ABC yang angkanya segitu itu digunakan untuk satuan tekanan itu apa dan satuan temperatur apa. You cannot use the number directly for any units of pressure and temperature. For example, maybe the units of pressure will be ATM. Maybe the temperature unit will be Kelvin. Or maybe the pressure will be Pascal, but the temperature is Kelvin. Or this is ATM, this is Fahrenheit, for example. Then you can, after you finish the equation, you solve the equation, you get the value of pressure, and then you can convert it into other unit. Okay, this is normally end-to-end equation is used to have or to calculate the saturated vapor pressure. Ya, jadi biasanya persamaan Antoine itu digunakan untuk mendapatkan tekanan uap jenuh. Jadi dari satu zat, from one pure substance. If you know the temperature, or you can inverse the equation actually. So at 1 atm, for example, pada 1 atm, at 1 atm, what will be the saturated temperature? Yeah, you can get the value from this Antoine equation. You just use different approach. So you know the value of pressure, you have the value of the constant A, B, and C, then you calculate the value of temperature. It's the same. You can use the same equation. Whether you want to find out the pressure, if you know the value of temperature, or you want to find out the value of temperature if you have the value of pressure. Okay, please bear in mind that this equation is to get the value whether saturated vapor pressure or saturated temperature. Normally, the one that you need to find is saturated vapor pressure. This is for pure substance. Then, for example, if you have a mixture of fluid, for example, air. Air is consist of nitrogen and oxygen. This is 79%. This is 20%. Sorry, 21% then. Okay. This is supposed to be mass fraction or mole fraction. Anyone remember? If the value is around 80 and 20, is it the mass fraction, percentage of mass, or percentage of moles? Ada yang ingat nggak?
Moles, sir.
Moles. Okay, so if it's already in moles, then you can use this number to calculate the vapor pressure of air. So vapor pressure of air will be 79% times vapor pressure of nitrogen plus 21% of vapor pressure of oxygen. How to get this one and this one? You use the Antoine equation. Then the vapor pressure of air at certain temperature, so the temperature should be the same. For example, at 25 degrees C, you get the PV of nitrogen and PV of oxygen at 25. Then multiply it each by the mole fraction, then you get the vapor pressure or saturate, we call it vapor pressure of air at 25 degrees C is using this equation. Okay, any question until this part?
Sir, I have a question.
Yeah.
Is the saturation temperature the same thing as boiling point?
Yeah. Depending on the concept of the fluid that you use. Because if you, I think you already, later when you learn about the phase, if you just have one component, yeah, if you just have one component, the temperature, the saturated temperature and the boiling temperature will be the same. But if you have the mixture of component, if just one component, the profile, wait, I forgot, it's like this one, I think. Just one line. But if you have mixture of component, but later you need to confirm it with the thermodynamic class. If you have mixture of component, when you change when you change the temperature or you change the pressure, so the composition between the component is have different behavior, and it will be creating the area between pressure and temperature. Ya, jadi kalau fluidanya itu adalah fluida campuran ya, ketika nanti Anda merubah tekanan atau merubah temperatur, itu nanti komposisi dari zat tadi itu bisa berubah. Karena apa? Because each of the component has different boiling point, right? It has different vapor pressure. So at certain pressure, when you increase the temperature, maybe one component is already vaporized, but one component is still in the liquid phase, etc. So later you will have like area between pressure and temperature, and you are not calling it boiling point again, but one you can call bubble pressure, and once you call it dew pressure. Later, when you study the separation principle, I think next year for 2020 batch, you will discuss about it in detail. But in concept, yeah, the saturated temperature is similar to the boiling point. Even though at saturated temperature, not because if you say it's boiling point, normally you can see the physically the liquid is boiling, right? But for the saturated temperature, it's not necessarily boiling. Boiling means I think actually boiling is already if you have the liquid at certain pressure and at certain temperature for longer time, so it creates like boiling phenomena.
Oh, so it's about to boil, sir.
Sorry?
So it's almost about to boil.
Yes, yes.
Okay, I see, sir. Thank you.
Any other question? Okay, maybe the last one is still actually related to the ability of certain liquid, certain fluid, especially for the gas. Maybe in our first meeting class and also in regular class, Pak Yogi already explained why we keep the tank in in a sphere tank, sometimes because it's to compensate the ability of the fluid, especially gas, to expand. So if, for example, in LNG or natural gas operation or natural gas plant, that certain gas we need to compress. Gas is easy to compress compared to liquid. Yeah, so the compressibility is basically terms that quantify the ability or the easiness of certain fluid to change its volume due to increasing pressure. Ya, jadi kompresibilitas itu menyatakan kemudahan suatu fluida untuk diturunkan volumenya karena kita menaikkan tekanannya. Basically seperti itu. So the quantity that express the fluid volume change to pressure change. So the degree of ease of a fluid to be compressed. For the gas liquid, it will be very, very easy. So in gas fluid, the distance between the molecules is very, very far. Ya, jarak molekulnya akan sangat-sangat jauh. So it means you have room to make the distance is closer. The distance closer, how? By increasing the pressure. Okay, by increasing the pressure, the distance is closer, the volume is reduced, and at certain point, the phase is changed from gas into liquid. So liquefied gas basically is a gas that you increase the pressure and lowering the temperature, and then you have the gas in liquid form with lower volume for the same amount. It means you can store lots of gas. Ya, jadi fungsi dari kenapa gas itu dicairkan, karena gas itu mudah dimampatkan. Jadi dia dimampatkan sehingga Anda bisa menyimpan gas dalam jumlah jauh lebih banyak dalam bentuk cair. So when it's compressed, normally you can increase the volume until 300 or maybe more, 500 times of volume. So it means when you expand, so the opposite of compress is to expand. When you expand the liquefied gas, it will expand until 500 volumes, 500 times of volume. So we call the gas fluid is compressible, or the compressibility is high. It means it's very significantly influenced by pressure and temperature. While for the liquid, it's low compressibility, and we call it incompressible fluid. Incompressible fluid means you cannot reduce the volume significantly by increasing the pressure. Ya, jadi untuk gas itu akan sangat mudah dikompresi, artinya volumenya akan sangat mudah diperkecil dengan menaikkan tekanan atau menurunkan temperatur, tapi efek tekanan lebih besar. Sehingga gas itu disebut dengan fluida compressible. Artinya gas itu sangat terpengaruh secara signifikan dengan perubahan tekanan. Beda dengan cairan. Cairan itu mau dinaikkan tekanannya, biasanya pengurangan volumenya itu sedikit. So we call it incompressible fluid. So later when we are doing the sum of the calculation, we can assume that for the liquid, the volume will remain constant even though we increase the pressure. While for the gas, the volume will be significantly reduced, or it will be significantly changed if we reduce or increase the pressure or the temperature. Okay. I think for the calculation, I think you will have more experience in thermodynamic class. So when we compress the gas, there are certain equation that you can use. This is the general equation from Boyle-Gay-Lussac, that the ratio between pressure, volume, and the temperature in each condition will be the same. So this is the interconnection between pressure, volume, and temperature. So like PV divided by T in every condition will be the same. And if you do the compression isothermically, it means at constant temperature. So it means T1 will be equals T2, right? So you can use this simplified equation. We call it Boyle law. So the simplified version of this equation. Have you learned this one in thermodynamic class? Not yet?
I think not yet, sir.
Okay. Hopefully I think this is still the concept of the compressibility. Okay. So basically the same as the concept of the vapor pressure, you can use Dalton law, yeah, hukum Dalton, to calculate if you have if you have mixed gas consists of several components of gas, then the pressure of mixed gas is basically the summation jumlah, ya, the summation of each gas pressure. So for example, you have air. Air, you have nitrogen, you have oxygen. This is two main component. If we assume that air is only mix of nitrogen and oxygen, then, for example, you have this one is 0.3 atm, this is 0.7 atm, then the total will be 1 atm. So basically, the pressure for mixed gas is the summation of each gas pressure. We call it partial pressure. And how to get the partial pressure? If you have this total pressure, yeah, the pressure of mixed gas, if you know the value of mixed gas pressure, and to get the partial pressure is multiply the total pressure with the mole fraction. So if you have air pressure at 1 atm, so it should be 0.8 atm, it should be 0.2 atm. It's because it's like 80% and this one is 20%. Okay, any question until this part? Okay, related to compressibility, this is the last part of this part one. So basically, if you are dealing with the ideal gas, this is the equation that you will use, right? So remember again, ideal gas, what will be the assumption? It will be in very high pressure, in very low pressure and very high temperature, when the interaction between the molecules is negligible. So you can use ideal gas, or certain gas is also follow ideal gas behavior. It means the compressibility of the ideal gas will be very linear, right? I mean, because the relation between pressure and the volume, when you compress, when you increase the pressure, you reduce the volume, right? The principle of the compression is like that. Ya, jadi prinsip kompresi itu kan Anda menaikkan tekanan untuk menurunkan volume, sehingga Anda bisa menyimpan volume dalam jumlah lebih banyak lagi gitu ya, dalam satu tempat. Ya, oke. Jadi untuk gas ideal, rasio antara P dengan V itu kan akan selalu konstan. Ya, sebanding, mengikuti persamaan gas ideal. Then how about the non-ideal gas? Basically, we can use the term of the compressibility factor. So the ratio between P and V will not be as the constant of the ideal gas. And this compressibility factor will be affected by the temperature. So there's certain value of the compressibility factor. So basically in thermodynamic class later, you also learn how to use this compressibility factor to calculate the value of maybe pressure or maybe the volume at certain temperature. Or maybe you can calculate the temperature at certain pressure. Even though you can check the value, yeah, it will be varied along the temperature and the pressure. Ya, jadi kalau untuk gas ideal, P dan V-nya kan akan selalu konstan ya, tergantung temperaturnya. Rasio P dan V itu akan selalu konstan. Kalau Anda naik, tergantung temperaturnya. Oke. Tapi kalau bukan gas ideal, ada faktor tambahan yang namanya faktor kompresibilitas. Sometimes it will just write P equals Okay, sometimes just like this. PV equals ZRT. So the moles is already included in the factor. And it will be varied according to the pressure and the temperature. This is the pressure in the temperature. So for example, if you have air, this is air, right? Read carefully the title. Okay, this is for air. The unit of the pressure will be in bar, absolute, or the unit of the temperature will be in Kelvin. Then, for example, if you have the air at 100 Kelvin and 20 bar, so the compressibility factor will be around 0.09. Okay, it means you can use this value to have to estimate later what will be the volume of the air at that condition. But if you increase the temperature, you will see that the compressibility factor, even though the pressure is still the same, right? 20. But if you increase the temperature, you will see that the compressibility factor is also increased. So at that temperature, the volume will be increased. But it's not linear as ideal gas. Ya, jadi tetap akan naik ya. Faktor compressibility-nya naik, temperaturnya naik, maka Anda bisa hitung berapa volumenya. Nah, tapi ini tidak akan selinier kalau menggunakan persamaan gas ideal. Kira-kira penggunaannya seperti itu. Any question? Okay, if you do not have any question, then I think this is the end of the part 1. So on next Wednesday, right? Or Thursday? I forgot Thursday, sorry. Next Thursday, we will discuss about the fluid static for the part 2. Okay, thank you everyone and good morning.
Thank you very much.
Thank you, sir.
Thank you, sir.